Okay, hello class. This lesson is just a continuation of our look at electrochemistry. Previously we looked at reaction equations where certain elements were becoming charged and other elements which were already charged were becoming neutralized, and we were able to spot redox or oxidation reduction processes whenever we saw single displacement was a real giveaway. A metal element coming into presence of a compound and displacing it, causing a new element and a new compound with changes in charges. So when we look at these reaction equations here, the practice set from section 2, we find that not many of these reaction equations are single displacement, and yet many of them are redox reactions. So we have to expand our understanding of what oxidation and reduction is a little bit more beyond just a change in charge for two or more elements. And in this section, this lesson video here, we're going to be looking at oxidation numbers. This is a way that chemists can look at elements involved in a reaction equation to identify which chemical is being oxidized and which one is being reduced. Now, oxidation numbers, it's a tricky thing to define, so I use the textbook summary here just to make sure I clearly present what the oxidation number is. It's described as the apparent charge that an atom would have if it gained or lost its bonding electrons. That does not mean that it has to be charged. We will use oxidation numbers to track the gain or loss of electrons in a reaction. We will use them to identify if a chemical reaction is in fact oxidation or reduction. And at the simplest way to present oxidation numbers, we can at the outset say that reduction involves a decrease in the oxidation number, and oxidation involves an increase. This is consistent with our previous definitions of oxidation and reduction, where oxidation was loss and reduction was gain. And we may have used Leo the tiger says grr. So this one, or Leo the lion says grr, has a similar meaning to it. Here, loss of electrons does increase the charge on something. Loss of electrons may just actually increase the oxidation number, even if there is no change in charge. And we'll see some examples that help us to understand the difference between oxidation where we actually have charges involved and just oxidation where we just have a change in the state or form of an element. By that, I'm referring to the oxidation state. All right, let's get started here and look at some of the rules. Now, these rules here seem intimidating when we first look at them. Let's look at them one at a time, just to understand this concept of oxidation numbers. So the first rule is that, as before, elements in their natural state, uncombined with anything else, they have no charge. Now we're going to say the oxidation number is 0. Okay, so not only is their charge 0, but their oxidation number is 0. So we could have potassium in its elemental form, we could have hydrogen in a diatomic, we could have phosphorus or sulfur in an elemental state. They'll all have an oxidation number of 0. Second rule, oxidation number of a simple ion is simply the charge of that ion. That's easy. If it's a calcium ion or an oxide ion or an aluminum ion, the oxidation number is consistent with the actual charge that that atom has after it has gained or lost its bonding electrons. So in the case of the formation of an ionic compound, sodium has one valence electron, gone. There goes the electron. Now, sodium as an atom has an oxidation number of 0 in its elemental state. the new particle is going to be a sodium ion with a 1 plus charge, and we would now identify that that particle has a +1 oxidation number. I'll try to be more consistent with my order with the positive, negative, and the number. When we're representing the charge on an ion, we'll put the amount of charge first, followed by the sign of the charge second. And when we want to represent an oxidation number, we will use the sign of the oxidation number first, followed by the magnitude of the oxidation number afterwards. So the blue numbers that I'm showing here are oxidation numbers, and the red is the charge, or ion charge. Okay, so in this case, pretty straightforward so far with these first two rules. Ions have charge, and their charge is their oxidation number. Atoms have no charge, their oxidation number is 0. Let's look at some specific elements. So hydrogen in most cases has an oxidation number of +1. So in the compounds water, dihydrogen sulfate or aqueous hydrogen sulfate, we have hydrogen with an oxidation number of +1. Also in the compound ammonia. Some exceptions here would be that metal hydrides have an oxidation number of -1 for hydrogen. So usually when hydrogen is paired up with nonmetals, it has a lower electronegativity, it loses its electrons, or it shares them unequally and has a positive dipole. And so with the molecule ammonia, we can sort of appreciate that. There's no charge in this molecule, but the hydrogen atom, again, what charge would it have if it gained or lost its bonding electrons? Well, remember polarity. Nitrogen is negatively polarized slightly because of its higher electronegativity. Hydrogen is positively polarized. So what would happen if hydrogen were to lose its bonding electrons? Well, it would have an oxidation number of +1 because it would develop a charge of +1. It would have one fewer electron than it had before. In the case of metal hydrides, pairing up hydrogen with a metal, which has an even weaker electronegativity, hydrogen would actually gain the electron. So in some metal hydride compounds, sodium hydride, the oxidation number we have to take note for hydrogen is -1. Fourth rule is for the element oxygen. For oxygen, in most cases, its oxidation number or oxidation state is -2. If we look at some molecules, water, nitric acid, these are molecular compounds. There's no ions in them in their pure form, so there's no charge, but should the oxygen atom gain its bonding electrons, it would have a parent charge of -2. So in the case of the water molecule H2O, we would have oxygen bonded to two hydrogens. What would happen if oxygen gained its bonding electrons? Well, it's more electronegative than hydrogen, so it would, we could say, steal those bonding electrons from each of the hydrogen atoms, and it would have a charge of -2. Now that's not what happens in the water molecule. They're neutral molecules. There is no ions within the molecule, but if we kind of extend the idea of electronegativity and sharing of electrons to what would happen if the more electronegative atom gained, then that would help us to determine what the oxidation number is. Now in the case of peroxides, so hydrogen peroxide, that's the exception for the element oxygen. Its oxidation number there is -1. Now again here, just to help you understand this idea of this apparent charge. Now, hydrogen peroxide is H2O2. So its Lewis structure would look like this. And I'm going to draw these just to kind of reinforce this idea of the apparent charge. Here, oxygen is more electronegative than hydrogen, and so it's delta negative relative to hydrogen. Now, clearly, oxygen would not steal an electron from another oxygen atom, because that would be like two people having an arm wrestle and they're exactly equal in strength. There's no gain either way. The only electron that could possibly be transferred, if we can even imagine that, would be from hydrogen to oxygen. So the oxygen atom would gain, in this case, only one electron, and it would have a -1 charge. So that's why the oxidation state or oxidation number for oxygen in the peroxides is -1. And in this case, no difference for the oxidation number for hydrogen. Here it's still +1. Okay? So there are some exceptions to oxidation numbers for elements, and we just memorize these exceptions and we apply them in chemical reactions where we see peroxides. Now, moving on, rule number 5. The oxidation number of group 1 element ions is +1 and group 2 element ions is +2. That's kind of a no-brainer, and that's sort of consistent with rule number 2. Because here it says the oxidation number of a simple ion is the charge of the ion. Rule 5 is just stating that we can know that if we look at the periodic table, anything that is an alkali metal will have an oxidation number of +1, and the alkali earth metals would have oxidation numbers of +2. So there's some examples given in the second column. Rule 6. Now this is where we start to get into compounds, and the fact that a compound doesn't have an overall charge. This is consistent with having an overall sum of 0 for all oxidation numbers. So here, within a molecule, if we were to add up all of the oxidation numbers according to the number of particles of each element, we would find that it would total 0 for every compound. Now, I want to say the obvious extension of that is that if the particle is polyatomic but has a charge, the sum of oxidation numbers in a polyatomic ion would equal the charge of the ion. So for example, the hydroxide ion, we know its ion charge is 1 negative, and here we would look at the sum of all oxidation numbers would equal that value. So we can apply these rules in some examples here to look at how to make sense of this term oxidation number, and specifically how we can use it to identify the presence of a reduction or oxidation pair of reactions. Now remember, not every chemical reaction involves oxidation reduction, and so try to appreciate that in the context of all the types of reactions that we've learned. This is just one of a category which probably includes some of the other types that we've learned. Single displacement, we've seen for sure, involves oxidation reductions. Double displacement may not always involve oxidation reduction, but sometimes it might. Decomposition may sometimes, may not. So we have these rules here now to be able to apply to see if in fact there's any change in oxidation numbers. And if there is a change in oxidation numbers, we can take that to mean that there is must be a loss or gain of electrons in the reaction, and there must have been an increase or a decrease in oxidation number. In the first practice example here, we have just simply determine the oxidation number of each element in each of the following compounds or ions. So remember, for oxidation number, we're going to put the positive or the negative first, followed by the number. Okay. For ion charges, we do the opposite. We put the number followed by the positive or the negative. Now, elements oxidation number is 0. So chlorine, both atoms have an oxidation number of 0. Of course, the oxidation number for the same element has to be the same. Oxidation number for the element hydrogen, well here, sulfur we're not certain of, but we can say it's probably like oxygen, it's -2 most of the time. Hydrogen, we're told, is +1 most of the time, unless it's involved in hydrides. This is not a hydride, sulfur is not a metal. So because there are 2 hydrogen atoms, then we would have to have a -2 oxidation number on sulfur. If we were to look at, again, sulfur is an element, so its oxidation number is 0. Fluoride is an ion, so its oxidation number is equal to its ion charge. Sodium oxide has an oxidation number on oxygen of -2, so that must have a oxidation number of +1 on the sodium ions because there are 2 of them. So we're kind of combining the rules for group numbers and oxidation numbers with the sum of oxidation numbers in a compound being equal to 0 here as we go along. Carbon dioxide is a compound, so there's no charge to it, but we do have, again, oxygen has a oxidation number of -2 most of the time. This is not a peroxide. So, because there are 2 of those atoms in this molecule, the total oxidation number for the oxygens is -4. So that would have to be combined with an oxidation number of +4 for the carbon. Now I'll start to just label these to make sure that we're clear on which element I'm referring to. For G and H, here, just note this is a peroxide. We've already looked at this example, so this is hydrogen with a +1 oxidation state or oxidation number, and there are 2 of them, and so that has to be balanced with a -2 oxidation total for the other element, and there are 2 of those, so it would have to be +1 and -1 for hydrogen and for oxygen. In the case of iron 3 oxide, so here we have iron, which is not a group 1 or group 2 element. We have oxygen, which is not a peroxide compound in this case. So we can look at sort of a little formula here. We have the total of oxidation numbers is 0. We have 3 things that we know have an oxidation number of -2, and we have 2 things that have some unknown oxidation number. So we can kind of call it maybe generally X. So sometimes we can set up an equation to solve oxidation numbers here. -6, 2x plus -6 is 0, so x must be equal to +3. And of course, that's in line with what we know the ion charge for iron to be in that compound. Now keep in mind, this is an ionic compound, so we actually maybe could have made it a little simpler by just looking at what is the charge on the ion for each of those elements. And here, going back to rule 2, the oxidation number of a simple ion is the charge of the ion. So the 2 simple ions in that example would be the iron 3+ and the oxide ion. In number 2, here we only have 1 element that we're trying to isolate, and the thing to note is that for some of these there are polyatomics. So for C and E and H, the polyatomic ion charge needs to be used. The way I would look at solving these is to look at the elements that we know oxidation numbers for, start with that, and if it's a compound, the total oxidation number must be 0. If it's a polyatomic ion, the total oxidation numbers must be equal to the ion charge. So let's look at hydrogen chlorate. So here we have hydrogen at oxidation number of +1. We have oxygen with an oxidation number of -2. And we have chlorine with some unknown oxidation number. So let's list what we know and then write a simple little equation. So we have 1 hydrogen, 1 chlorine atom, and we have 3 oxygen atoms. So that's the total of all the oxidation numbers, and here for a compound it's equal to 0. So we basically have 1 subtract 6 plus x equals 0. So negative 5 plus x equals 0. And you're just probably shaking your head here that we're doing math and chemistry again, but here's how we apply math, is just to situations where, you know, we need to work with some numbers. So the oxidation number for chlorine here is plus 5. Chlorine is not charged with plus 5. It has not lost 5 electrons, but that is the number that we're assigning to chlorine in that compound, assuming it was to gain or lose its bonding electrons. Now I'll just go through this one example here just to try to help you make sense of this. What does hydrogen chlorate look like? Well, it's hydrogen bonded to chlorine, bonded to 3 oxygens. Okay, and we start out with all the Lewis symbols for each. And there we are. Now, it's not, no charges are involved here, so there's no electrons been gained or lost. We have to make all these bonds work with what's available. So we'll pair up these. There's a bond. Now, in the 4C section, when we were looking at covalent bonding, we didn't look at coordinate covalent bonding, but that was a type that the 3U's looked at. And it's kind of important that we understand that a little bit here, because here what happens is chlorine with 3 pairs of electrons actually coordinates or assists oxygen in getting its octet. And so oxygen needs 2 more electrons, and rather than sharing, in this case, it does share, but it doesn't contribute any to the bonding pair. So basically chlorine right now, as I've shown, is hydrogen chloride. It doesn't need any more electrons. So it can't share anymore from the oxygen, so what it does is it coordinates each of its pairs here to the oxygen atoms. So what that allows for is it allows for oxygens to have their full octet, allows chlorine to have its full octet, and hydrogen has 2, which is stable like helium. Now I'm mentioning this because to understand this oxidation number of plus 5, let's look at all of the possible bonds. We have chlorine-oxygen bonds, and we have hydrogen-chlorine bonds. Now, hydrogen is the least electronegative of the 3 elements, so it's delta plus. Now, of the 2 remaining elements, chlorine is, I believe, less electronegative than oxygen. So actually, oxygen relative to chlorine is delta negative. Now that's a little bit strange, because here, when we put our dipoles on, they're kind of relative to 2 elements. So the HCl bond would be delta plus with hydrogen and delta negative with chlorine, but when we look at the chlorine oxygen bond, it's actually delta plus for chlorine and delta negative for oxygen. So, all right, what's going to happen if the electrons could be gained or lost between chlorine and oxygen? Well, oxygen would get them. So that has chlorine losing 2, 4, 6 electrons to the oxygens, which would give it a charge of plus 6, but it gains 1 back from being more electronegative than hydrogen. So what's the overall result? The apparent charge, if all electrons were transferred to the most electronegative element, would be chlorine would end up with a apparent charge of plus 5. Okay? Now, not changing the rules for bonding. This is still a covalent molecule. Electrons are still being shared unequally, but there are no actual charges. But that's how we can understand oxidation number here. It's to sort of draw a Lewis structure of the compound or the ion and just start to think about which way electrons would move in the bonds if they could. So here, the rest of these examples, this is a simple matter of setting up an equation, writing the total of the oxidation numbers either equal to 0 for compounds or the ion charge for ions, and solving for the unknown element. If we get in a situation where we have 2 unknown elements in our ion or compound, we're going to struggle a little bit with that. But I think in most cases here, we can use the predictable rules that we've already looked at here and go with the oxidation number for the simple ion from the charge. We can go for the known oxidation numbers for hydrogen and oxygen, and we can use the exceptions if they come up. Let's look at polyatomic ions. So let's say the sulfite ion here in C, we have sulfite made up of one sulfur atom and 3 oxygen atoms. The overall charge of this is 2 negative. So if I'm going to write my elements here, sulfur has unknown oxidation number, don't know. Oxygen has an oxidation number of -2. So this is what I know. I can write an equation. The ion charge is the total oxidation number, and here that's going to be equal to 1 sulfur atom and 3 oxygen atoms. So the total of the negative oxidation numbers is -6, and when we add -6 to x and we end up with -2, we have to be starting with +4. So that means that sulfur has an oxidation number of +4 in the sulfite ion. If we were to look at, let's say F, and we have iron 3 nitrate, we have iron, nitrogen, and oxygen here. We know this is an ionic compound, and if we reverse the crossover rule, we know that we have 3 nitrate ions and 1 3+ ion. So this ion would have to have an oxidation number of +3. The nitrogen is probably the one that we don't know. The oxygen in this case is not in a peroxide, so its oxidation number we can assume to be -2. And that leaves us with element nitrogen as an X question mark, which we'll determine by remembering that this is an ionic compound with an overall charge of 0. Remember that. It has 3 nitrate ions and 1 iron 3+. So the 3 times -1 and the 1 times +3, that's the balance of charges for the compound. Okay. So the total of oxidation numbers here would be equal to 0, and we take 1 iron ion at +3 for its oxidation state. We have 3 nitrogens. Now remember, the brackets applies equally to each of the particles inside. So we have 3 nitrogen atoms, and we actually have 9 oxygen atoms, each with an oxidation number of -2. So that gives us -18 and 3 added to 3x, totaling to 0. So we have -15 and 3x equals 0, and that means x must be equal to +5. So that would be the oxidation number for nitrogen in this. I'm not going to explain why it's +5 here. At some point we just have to appreciate that this is the oxidation number, this is the apparent charge that that atom would have if it gained or lost its bonding electrons. So review the 7 rules. Remember that at the end we want to determine if oxidation or reduction has occurred. So oxidation is occurring if there's an increase in oxidation number, reduction is for a decrease. And if we were to look at these reaction equations, now that you know how to identify the oxidation number for elements in a compound or an ion, now at this point it'd be a matter of looking at, are there any changes? So for example, in say G, methane. Now here this becomes a quicker process after a while when we start to use oxidation numbers. So oxygen is 0. Methane, carbon must be -4. Hydrogen is +1. In the product side, we have carbon dioxide. Here, carbon, oxygen is -2. There are 2 of them. there must be an oxidation number of +4 on carbon. Water has oxygen, hydrogen, oxidation number of -2 on oxygen, +1 on hydrogen. Let's look at what's happened overall. It appears that from the reactant side to the product side, oxygen has, let me just repeat here. So O2 has a oxidation number of 0, and now on the product side it has an oxidation number of -2. So that has been a decrease in oxidation number, so that must be a reduction. In the case of the reduction, that's 1/2 of redox. There must be an oxidation process. Can you spot it? Well, hydrogen is undergoing no change, so hydrogen as an element is not being oxidized or reduced, but we do see carbon going from a -4 oxidation number to a +4 oxidation number. So that would be an increase in oxidation number, so that must be oxidation. So in this reaction, wouldn't necessarily think of it like that, but this is an oxidation reaction, it's combustion. So there's got to be oxidation, and oxygen is what makes the oxidation happen. And you think of it that way, it gives you a little bit of a different appreciation for what oxygen actually does. It provides the necessary ingredient for something to burn or combust, but it actually causes the other thing to be oxidized. And here the other thing is the element carbon. So hydrogen, no change, carbon is being oxidized, and oxygen is being reduced. So as soon as we can spot two changes in oxidation numbers, we can say that that is a redox reaction. So that would be our conclusion. Okay, so we'll conclude at this point. This has been a longer introduction to this type of redox, but now that we understand oxidation numbers, we can look at any chemical reaction and identify if, in fact, oxidation reduction is occurring, even if we don't even understand the reaction type. Okay, so hope this has been helpful, and you can come in tomorrow and complete the practice questions in the set and then work on the ones that are in your handout listed at the bottom right here. Take care.